Hey guys, so in this video we're going to introduce the concepts of heat transfer, which should be a little bit of a review, and the concept of enthalpy, which is something that will be new for all of us. As we go through this video lesson, there are some vocabulary words to add to your flashcards. Endothermic, exothermic, enthalpy, enthalpy of formation, and standard state. And those will be fair game on any cold call quiz coming up in the future. So let's say that we have two gases. It's the same gas, and they're put into this contraption here. And on the left, the gas is at 100 degrees Celsius, and on the right, the gas is at 80 degrees. And we have these two valves here, which are little doors. And let's just say that we go ahead and we open those up. So these gases are now allowed to interact. What is going to happen? Well, we know that these gas molecules are going to move around randomly and they're going to eventually enter this tube and they're going to collide with the walls, but eventually they're also going to collide with each other. And when that happens, some type of energy is going to be transferred. Okay? How is that energy going to be transferred? Well, number one, it's going to be transferred in the form of heat. And the way that we will observe that is that energy, okay, or heat, the rule transfers from hot to cold. Hot to cold. So the hotter, higher temperature object will transfer energy or heat to the colder object. So in this case, the red gas molecule would bounce around, and if it collides with a blue 80 degree, oops, that's not blue, 80 degree molecule, some of this heat, the energy associated with this molecule moving, is going to be transferred to this blue one. So ultimately, the temperature of this red molecule will drop and the temperature of this blue molecule will increase. This process, energy transfer, occurs until you reach something called thermal equilibrium. And thermal equilibrium is exactly what it sounds like. Thermal, having to do with heat, okay? Equilibrium meaning equal. So at thermal equilibrium, there is no transfer of heat because objects are at the same temperature. All right? So the big theme is energy transfers from hot to cold until one of those objects warms up as it gains heat and the other one cools down until they reach the same temperature. So why is that important? How else can we model that? Well, there's two terms that we can use to describe these processes. One term is endothermic, and the other term is exothermic. Okay? Now, what's important to determine these terms is thinking about the prefix. Exothermic, I think of means exits, okay, or releases energy. Endo sounds like enters or adds. So in an endothermic process, something gains, adds energy. In an exothermic, something else exits or releases it. Now what's tricky about that is this all depends on your perspective. A process can be endothermic or exothermic depending on the perspective. So for example, let's say here, you're holding a hot cup of hot chocolate, for example, okay? And if you grab it, you feel, oh, that's hot. That feels warm to you. Now, why is that? That's because, if we were to draw a little model, energy is going from the cup into your hand. So I'm trying to draw it here from the white mug into your hand. So energy is going into your hand. So from your hand's perspective, this is an endothermic process because your hand is gaining energy. It's gaining heat from the mug, which is why it feels hot. However, from the mug's perspective, okay, from mug's perspective, this is actually an exothermic process because the mug is losing heat. It's releasing heat into your hand. So we can see is that it depends on if a process is endothermic or exothermic, what perspective we're looking from. Okay, and the words that we use to describe these is, are we looking from the perspective of the system or the surroundings. And whenever we're talking about chemistry, we're going to be talking about the system, which is the reaction, which you'll sometimes see abbreviated as RXN. We'll very frequently see abbreviated. So, if you have a beaker, okay, and some reaction is occurring, the way we determine if that reaction is endothermic or exothermic is by what's happening to heat from the perspective of the reaction. Is the reaction losing heat? Then it's exothermic, or is it gaining heat? Then it's endothermic. So the way to determine this, the easiest way, boom, 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 here's a thermometer. Let's say, A and B are mixed, and there's going to be a temperature change, okay? The thermometer here is not part of the reaction. It's part of the surroundings. It's not part of the system. So if we see the temperature increase, that means energy or heat is going from the reaction, A and B, into the thermometer, which is causing the temperature of the thermometer to go up. So if temperature increases in a reaction, that reaction is exothermic. That's the first big thing to know. On the other hand, if you mix two things together, okay, A and B, in the reaction, and you have a thermometer here, which is not part of the system, and we see that the temperature drops. If the temperature drops, then it's an endothermic process. And that can be sometimes tricky to think about because you think, okay, endo means that energy is being added, which means the temperature must be going up because it's gaining heat. But what is actually adding energy? Is it the system or the surroundings? If the thermometer is showing a drop in temperature, that means the thermometer itself is losing energy. Where's that energy going? It's going from the thermometer into the reaction. So since the reaction is gaining energy, that's what makes it endothermic. This is all very qualitative. Oftentimes we represent these with things that are called energy diagrams. And we need to know how to analyze these, interpret these to determine if reactions are endothermic or exothermic. We'll get into a lot more detail about them later, but for now, let's just say you have a reaction where A is turning into B, whatever A and B are. The way energy diagrams operate, what they show us is they show us the reaction pathway or timeline. So over here on the left, it's just like an equation. This is where your reactants are. Here's where the energy of your products are. On the y-axis, we can see we have PE, which stands for potential energy. Or we can just say energy in general. So we can see that here, when they're the reactants, A has 50 kilojoules, kJ, of energy to start. And the products, B, now look like they have 100 kilojoules of energy. So we need to think about, okay, did the reaction gain or release energy? Well, if it started at 50 and it ended at 100, it clearly gained energy. So this type of curve is for an endothermic process. And the best way to tell is your starting energy is less than your final. We had to add energy to this. So if the ending point is higher right here than my starting point, the process is going to be endothermic. Okay? On the other hand, if you had an energy diagram, which I'll just sketch here for the same reaction, and let's say it looked like this, now, we can clearly see that the products, B, have less energy than we started with. The energy dropped. This could be 50 and this could be 10. So there's less energy now than there was at the beginning, which means that this reaction must have lost some energy or released it. That's why this would be an exothermic process. So what we need to be able to do is with these diagrams just identify, is it endothermic or is it exothermic, and why, based on what's happening to energy. The other way to think about it is if we're trying to figure out the change in energy. Remember, delta always means what's the energy of your products, what you end up with, minus the energy of your reactants. And what we can see is we can prove this if we apply this to like the endothermic reaction. The energy of the products here was about 100 kilojoules. The energy of the reactants was 50. So 100 minus 50 is 50 kilojoules. And this is a positive number, which means that the reaction must have gained energy. That's why it's endo. Over here, on the other hand, the change in energy is going to be your final, which was about 10, minus your initial of reactants 50, which is negative 40, which clearly shows exothermic process because it's negative. Why is that going to be important? Well, because we're going to introduce the concept to quantitatively measure this energy, and that is with something that is called enthalpy. Okay? Enthalpy. Enthalpy is a new unit, okay, not a new unit, but a new quantity that is abbreviated with a capital H. Enthalpy is abbreviated as an H. And what enthalpy measures, it's the total energy in a system. It measures all the energy and all the different types and forms of energy in the system and allows us to predict if a reaction is endothermic or exothermic and how much energy will be given off. There's three things that you need to know about enthalpy. Number one is that it is extensive. What does that mean? That means it depends on the amount, AMT amount. So if you have, for example, 1 mole of methane, CH4, that burns versus 2 moles of CH4, different amounts of energy, enthalpy, will be released or gained because the amount is different. So it's extensive. It depends on the amount. Okay? Enthalpy for a reverse reaction switches the sign. So that means if delta H, the enthalpy of a reaction, is 50 degrees for A going to B, if we switch the reaction for B going to A, the enthalpy for that reaction, which we'll do as a different color here, is going to be equal to negative 50. It's the opposite if you reverse the reaction. And last but not least, enthalpy depends on state. It depends on the state of matter. So for example, the enthalpy of liquid water is not equal to the enthalpy of vapor as a gas. And that will become very important. So when we're measuring the energy change in a reaction, we want to look for these things. Okay? How does this connect back to our diagrams? Well, if something is endothermic, okay, that's because the reaction gained energy. So the change in energy, enthalpy, is going to be greater than 0. So this is the type of thing, if I say, what's the enthalpy of the reaction, and I say it's 50 kilojoules, you have to know, okay, since that's greater than 0, I automatically know that it's endothermic. On the other hand, if a reaction has a negative enthalpy value, negative 50, negative 100, you automatically know that it's exothermic because it released energy. So we need to associate the value, the quantity of delta H, with the type of process that's going on. How do we actually calculate these numbers? You know, here we're given a graph, but how do we actually calculate the numbers? How much energy can we calculate as gain or loss in a reaction? In order to do that, we use something called the enthalpies of formation. So any reaction that occurs, any product, any compound that's made, is going to gain or lose some energy. So in this table, this is just an example of a table that shows standard enthalpies of formation, which are going to be abbreviated as delta H, F, with this little naught here. Okay, we pronounce this naught, that little circle at the top. What this means, first of all, this will be a very common thing you'll see all year, this little circle, which means your standard conditions. And standard conditions for energy calculations are different than standard with gases. So STP, we learned, was, you know, a certain set of standard conditions. Standard conditions for enthalpy for energy reactions are always at 1 atm and 298 Kelvin. So all reactions are conducted at those conditions in order to normalize on how much energy is gained or lost. You'll see here that some compounds, when they're formed, release energy and some gain energy. For example, acetylene, it has an enthalpy of formation of 226.7 kilojoules per mole. Remember, per mole, it's extensive. It depends on how many moles that we have. That's going to change how much energy is released. So this is endothermic when this thing forms. On the other hand, when carbon dioxide forms, it's negative. This is very exothermic. Okay? There are some compounds that you need to know their enthalpies of formation because we have set a standard as chemists for what they are. So compounds that are in the standard state. And what that means is elements how they exist naturally at standard conditions. So for example, standard states are solids without a charge. So for example, if in an equation you see Mg solid, Ca solid, the standard state, the enthalpy of formation is equal to 0. It's an assumption that we make. This is not true if you have something like an ion, like Mg2+. That's not in its standard state. So the enthalpy of formation, the energy for this, is not equal to 0. Only if it's a solid with no charge. Other things to recognize, elements that are in their standard state are the diatomics. So if in a reaction you see something like N2, O2, H2, you need to know that the enthalpy of formation of those is 0 in their standard state. These compounds do not represent their elements in their standard state. That's why they're not at 0. But we need to use these in order to do quantitative calculations. So for example, here's a type of problem we need to do. Using the enthalpies of formation in the table, okay, so I'm going to need to use this table, determine the standard enthalpy change for the combustion of 1 mole of acetylene. So in order to do this, I'm given a chemical reaction. I need to figure out what is delta H equal to for the reaction, which I'm going to abbreviate RXN. Well, we know the delta H of a reaction, and we got to put the little knot here to indicate where it's standard conditions. Just like we said before is the products minus the reactants, it's the same thing. It's the enthalpy, change in enthalpy of the products minus the enthalpy of the reactants. And this is an equation that's on your equation sheet. The only difference that on your equation sheet there's a little Greek letter sigma here. Okay? And what this means is it means the sum, because we have to take into account if there's more than one reactant or product. So the way we apply this formula to determine is this reaction endothermic or exothermic, delta H naught of this reaction, because we're not talking about the formation of one compound, of the reaction, I need to first get the enthalpy of the products. So what are my products? I have CO2 gas and H2O. So I need to find those compounds in the table. So first I find CO2 gas. I see it's here at negative 393.5. And remember, since enthalpy is extensive, it depends on the amount, I need to look at the number of moles in the equation. It's 1 CO2. So this is going to be times 1 plus, because remember it's the sum, the enthalpy of water as a gas, not as a liquid, because notice here I have water as a liquid and as a gas. As a gas, it's negative 241.8 times, and in the equation, 1 mole. Okay? Realizing as I've made a mistake, guys, I forgot to balance this equation up front. So let's just go ahead and do that. To balance this equation, I'm going to need, I think, 2 moles of this, 5 moles of O2, 4 CO2s, and 2 H2Os. Now it's balanced. So now that means I need to go back here and make some changes really quickly, because this depends on the amount. How many moles of CO2 in the reaction? There were 4 from the coefficient, and from CO2, for H2O, there were 2. Okay? So that's the enthalpy that's from my products. Now I need the enthalpy of my reactants. Okay, so everything over here. 2C2H2 and 5O2. So in the reaction, it's there was a minus sign here. So minus C2H2 gas, let's find that in the table. C2H2 gas, 226.7 times how many moles of it? 2. Plus, now here's where you get a little tricky. O2. You're looking at the table, you don't see O2 anywhere. But remember, the enthalpies of compounds in their standard state, solids without a charge and diatomics, is 0. So the enthalpy of oxygen is going to be 0 times the number of moles 5, which is still going to be 0. So this is the setup. So now if I go ahead and do the math, the enthalpy of this reaction, I'm just going to show all my steps so I don't make any silly math mistakes, which is super common. Negative 393.5 times 4. 393.5 times 4 is negative 1574 plus negative 241.8 times 2, negative 483.6 minus 226.7 times 2, which was positive 453.4. So now if I go ahead and keep continuing to do the math, again, common mistake where students get these things wrong is just in the arithmetic. So be very careful with your negative signs. And we get negative 2057 minus 453.4. And we get a final answer of negative 2,511 kilojoules per mole in this reaction. So we know that number one, this is very exothermic because delta H is less than 0. Lots of energy being released. 2,511 kilojoules per mole of these reactants. So if we change the amount of this would change. So through this video, you want to be able to feel comfortable using this formula, which I'm going to rewrite on the next page. The enthalpy change in a reaction is equal to the sum of the enthalpies of formations of the products minus the sum, this is the sigma, of the enthalpy of the formation of the reactants. And then we just go ahead and plug in our values. This is on your equation sheet. We want to feel comfortable doing that, watching out for the number of moles from the balanced equation. Make sure it's balanced, unlike what I did in the beginning. Knowing our standard state processes, knowing that enthalpy depends on the amount, it switches sign if we reverse it, and it depends on the state, liquids and gas matter. Understanding energy diagrams and predicting endothermic or exothermic from these, as well as knowing that that depends on the perspective of the compound. And finally, knowing our vocab terms for heat transfer from hot to cold.